potential energy surfaces and properties compared to the p-wave states. Now, if you look at the inset over here, this is an inset which shows potential energy curves. Then you get a p-wave state coming down as a function of the internuclear distance, and an s-wave state, oscillatory behavior, crossing it. Actually, this is an avoided crossing, so they don't really cross, they avoid each other. But what happens is that unfortunately, this crossing happens at a distance where practically you're in equilibrium for the S state. But if there is a crossing close to an equilibrium, means that the system typically or generically becomes unstable. Yeah? So this is one comment. Now, if you switch on electric field, something very favorable happens to your system. Essentially, you keep the positions of these minima, but what you do, and what happens with increasing electric field, these are three curves with increasing electric field, you not only shift the curves, this is one issue, you make an absolute shift in energy, but you make a relative shift of the different minima. You see, this minima sequence goes up in energy. This one at the next field strength is almost at equal energy, and then it goes down. So with the electric field, you have an option to sort of change the positions in energy of individual wells with respect to each other. And in particular, you get rid of this crossing, which leads to instability. So that means the electric field tends to stabilize the system, it deepens the wells, and makes the well structure of the trilobites more pronounced. Yeah. If you go to the extreme for very high fields, and this is not clearly shown here, what happens is that this state down there, which practically looks constant as a function of energy, which is way off from these states, if you increase the electric field, this state moves further down and finally crosses or shows avoided crossings with this 38S state. A specific state which is a quantum defect splitted state from the degenerate manifolds. So then what happens is that you get an avoided crossing with this 38S state, and that mixes components of this state to the eigenstates involved in this avoided crossing. Now, let me explain a little more what I have been trying to show to you over here, what the impact is of the electric field. Now, what you see here as a function of the electric field, the dipole moment, and in the inset you see the equilibrium, which this is kind of read, of course. This is the electric field axis, and this is the equilibrium position. If I enhance the electric field, as you see over here, subsequently the global minimum of the system is here, then it is here, and then it is here, with increasing field. This you see over here, this is just this plateau step-like structure in the equilibrium position. Yeah, this is just the change of the equilibrium with electric field. Now, the dipole moment itself, of course, reflects this too. This is a comparison between exact and semi-classical approximation for this dipole moment. So what happens is that the dipole moment, for every crossover of the global equilibrium position, shows also this plateau step-like structure, and it goes to larger values of the dipole moment because we go out here from one minimum to the next minimum. Now, I want to draw your attention to one more feature that is over here. That is, if you go to very strong electric fields, finally the dipole moment decreases instead of increasing. Yeah? Now, this comes from the fact which I indicated already. This is if you go to these if you go to these very large electric fields, then finally you have avoided crossings with the 38S state. And that admixes, since it is an S state, low angular momentum components to your state. And that is why finally this dipole moment starts to decrease. Yeah? This you can see over here. What I just argued physics-wise appears here in the eigenstate analysis. Now this is the stick spectrum of the participation of the basis states, yeah, in the true eigenstate. You see you have this certain distribution, and the 38S state for this field strength, which is comparatively low, is not contributing a lot. This would correspond to the situation over here or over here. Now, if you go to high field strength, 600 volt per meters, you see that you get a significant contribution from the 38S state. And this is then contributing to a decrease of the dipole moment for large field strengths more than 600. Okay, so this is a final picture on this behavior of the trilobites in electric fields. This shows you just how the different vibrational levels in these multi-well potential energy curves look like. This is as a function of the electric field, the different vibrational levels, and you see every time you have the crossover between these different potential curves, you get these dips in the vibrational structure due to a delocalization of these vibrational states in the potential energy surfaces. Okay, so let me conclude on that part. I don't know how much time is.
About 15 minutes total.
Okay, fine. That's fine. So, first of all, we have a very nice controllability with the electric field on the trilobite states. We can nicely tune the potential energy surfaces. And then there's also this hope that you might prepare these states now with a two-photon excitation scheme, which has only 2 angular momentum units available, because if you go to strong electric fields, then you can go directly to the situation where the 38S state is admixed to your system. And then you can finally also have this P-wave intersection removal, so you shift the global minimum to larger distances and deeper wells. Okay, so that was the first part. Now let me come back to what I've been describing to you yesterday. This was on these giant dipole atoms. The strongly decentered exotic system that has its electron being localized far away from the atomic core and doing some vibrations in this outer well, which I have been trying to describe to you. Let me briefly rush through these, what we had yesterday. These are 3 transparencies now, which just repeat what I've been saying yesterday. We have this gauge-independent formalism in the pseudo-separation of the Rydberg atoms. We have this gauge-invariant potential, which leads to the decentering. Yeah? And this decentering creates this outer potential well. This outer well has the electron in it, and the positive core is sitting in this Coulomb well. It exists if you exceed the electric field beyond a certain critical value, or alternatively the pseudo momentum, and that leads to these states which live in this outer well. And characteristic of these states, I'm talking about the decentered Rydberg atoms at the moment. Characteristic of these states is a megahertz spacing of these states, a huge electric dipole moment, and this is strong field physics. Okay, this is not 10 Gauss, this is a few Tesla physics. So, but you have here also strong variability with changing parameters. This is what I was talking about yesterday. Okay, now the idea is, what if you take this decentered atom and you allow yourself to put a neutral perturber additionally to the electronic wave function into the outer well? Then, according to what I've been describing to you, electron-neutral perturber scattering, there might be the possibility to bind the neutral perturber to the electronic cloud. This would mean you would have a giant molecule, a giant decentered dipole molecule. Okay, let's look at this, what happens. So what we have is this electron which is out there. This has a kinetic energy and it has a potential energy according to this potential double well structure. Then this electron scatters from a neutron. This is this interaction. It's at very low energies. You are very far from the nucleus. You do not need to take into account P wave. P wave is completely negligible. S wave is totally fine. And even the effective range is essentially for low excitations not necessary. You're in the limit K goes to 0. If you go to higher excitations, it might become, or it will become relevant there. The methodology, you do exact diagonalization, or you could do perturbation theory, and for low excitations, both agree nicely. Now, what do you get? Let's take a typical setup. Let's take a 2 Tesla field on 50 volts per centimeter electric field. Then, for the decentered giant dipole atom, you get these kind of frequencies. Remember, yesterday I was discussing these modes which exist in the outer well. There was 2 different frequencies, 2 different modes, 3 different modes, 3 different frequencies. The one was the cyclotron of the light particle, the other one was the cyclotron of the heavy particle, essentially, and it had a Coulomb mode along the magnetic field. These are the 3 numbers for this case. Now, if you put that neutral perturber in this electronic cloud, and what you expect is that the lowest electronic state in the outer well is something like a Gaussian. It is indeed. Then what you get is a potential energy surface for this neutral molecule, which is out there, a potential energy surface which is a Gaussian behavior. So it's just like a Gaussian value. And in there you have vibrational states. And this is a 3D plot. This is X, Y, and Z. How this looks like, a color plot in 3 dimensions. And now this kind of electronic cloud traps the neutral atom. So this is a trap, a decentered trap for the neutral atom. It's a giant dipole model. So now, but the difference here to the normal or trilobite or whatever states, there's many differences. This has only 1 minimum, but it cannot decay radiatively. There's no radiative decay in the outer well. Yeah, this system, if there is no collisions with others, lives forever. Tunneling is negligible for this. So this is stable, ultra long-range molecules, decentered. And it is many wells, it is a nodeless surface. So it's a trapping of a neutral in this decentered state. Now, if you go to excited states, the topology, according to the excitations in the outer well, become quite intriguing. Yeah? Now, this is the first excited state. These are 2 different plots for the first excited state. This is, again, an X, Y, Z, 3-dimensional plot. And what you see is it's like a kind of a torus. Now the neutral is captured in a very cute trap, namely a torus configuration over here. If you do the 2D XY energy plot, this looks like, of course, like a Mexican hat, because the inner part is repulsive, and you're allowed to move around this inner part. So this is the trap for your neutral atom now. Now if you go to higher excitations, like this is the 5th excited state, then there is avoided crossings taking place. As a function of the coordinate of the neutral, avoided crossings between these 3-dimensional potential energy surfaces now. And this is how it looks like, so it's quite intricate topology. Now, if you look into it from an intersectional point of view, you see that you have intersecting 3-dimensional surfaces among each other, and this is a 1-dimensional intersection, so you see how 7th, 6th, and 5th excited state intersect with each other or show avoiding crossings and deform each other's topology of the potential energy surfaces. So this brings me to the end. In this case of the decentered ultra-long-range molecules, one might be tempted to follow the route which we have been suggesting in order to prepare the decentered atoms, maybe combined with radio frequency transitions in the outer well. Certainly the ultra-cold environment is an ideal setup for this. And again, this is now saying, okay, we have giant dipole molecules. The question is maybe we can form clusters, aggregates, or whatever you want to call these combinations of giant dipole molecules out of that. And that brings me to the end, and I would like to thank you for your attention.